First, we need to talk about a capacitor. A capacitor consists of two plates with opposite charge. A capacitor is used to store charge and energy. The capacitance is going to be labeled with a C. It's the capacity of a capacitor to store charge. So capacitance is going to have units of farads, which will be represented by an F. So everything in parentheses is a unit. K is going to be the dielectric constant. It's the insulator between the plates. And we'll talk about that in the next slide. E naught, we've seen this value before. It's the permittivity of free space. It's equal to 1 over 4 pi times K, which is 9 times 10 to the 9th. A is the area of one plate. Again, this is going to be a meter squared. And D is the distance between the two plates. Again, a unit of length, so in meters. Again, a dielectric constant is an insulator placed in between a capacitor. So here we have a picture of a capacitor, which again is just two plates. Each of them has the same charge, Q. And over here we have a capacitor with a dielectric in between. Again, a dielectric is just a constant, and this constant is going to have a value of K. Now, when we first started talking about capacitors, we're going to talk about the dielectric constant K is equal to 1. This is true for a vacuum, meaning no air. But when there is air, it's still very, very close to K is equal to 1. So we're going to assume that it's equal to 1 in both situations. So if a problem does not mention a dielectric, you're going to assume that K is equal to 1. Again, what this dielectric does, it prevents charges from moving between the plates of the capacitors and are constructed with an insulator between the plate. Now this part is very important. We can talk about increasing the capacitance, but this all has to happen before the capacitor is created. Remember that capacitance is set at the factory. So these changes can only happen before the capacitor has been created. So if you want to increase the capacitance, you would have to either increase K. This is done by using a stronger insulator, increase A, again just increasing the area of the plates, or you can decrease D, meaning you can put the plates closer together. So once a capacitor is manufactured, the capacitance C becomes a constant. So the amount of charge stored on it will depend on the voltage added to it instead. If we know the capacitance, then we can solve for the charge stored on the capacitor. Now we can use the equation C is equal to Q over V, where C is a capacitance. Again, this is units of farads. Q is the charge stored on the plate. Again, units of coulombs. And V is voltage across the capacitor, units of volts. So again, most of the time you're going to be asked to solve for the charge in the capacitor. So it's convenient to rearrange this equation and memorize it as Q equals C times V. The other very important part is that the charge stored on the plates is opposite and equal. So we mentioned earlier that if we have these two plates and you have a charge of 2 coulombs, what that means is that one plate will have a positive 2 coulomb charge and the other plate will have a negative 2 coulomb charge. Again, you wouldn't say that it has 4 coulombs, it simply has a charge of 2 coulombs. So when we start talking about charges on capacitors, then we can start talking about the energy stored on a capacitor. To solve for the energy stored, we know that energy is represented by a U. So we have U is equal to 1/2 Q times V, which is also equal to 1/2 C times V squared. Again, these two variations just come from using the equation Q equals C times V. So you can either just memorize one and derive the other, or vice versa. Again, U is going to be energy in joules, C is capacitance in farads, Q is charge in coulombs, and V is voltage in volts. Now, the very important part is that you do not confuse this with potential electrical energy. This is not the equation, and these are not equivalent to each other. Again, this is the energy on a capacitor. This was the energy of a charge in a potential. So let's try this example. We have a capacitor that has a plate of area 1.0 times 10 to the negative 4, and the plates are 0.2 millimeters apart. Again, to make sure that we have that in a number that's useful, we have to move our decimal 3 places to the left, and that becomes 0.0002 meters, or 2 times 10 to the negative 4 meters. And we're asked to determine its capacitance. Again, a dielectric was not mentioned, so we're going to assume that this has either vacuum or air in between it. So, to solve for the capacitance, remember it is K epsilon naught A over D. Again, our capacitance is equal to 1, and our epsilon naught is 1 over 4 pi times K. Our area was 1 times 10 to the negative 4. And the distance between these two plates was 2 times 10 to the negative 4. Put on that in your calculator, and you get 4.4 times 10 to the negative 12. Now, since we are solving for capacitance, that's in units of farads. Or you could also rewrite this as 4.4 picofarads, which is 10 to the negative 12. Now, this capacitor is connected to a 6-volt battery, and we want to determine the charge stored on it when it is fully charged. When it's fully charged, that means that the voltage across the capacitor will be equal to 6 volts. So, Q is equal to C times V, or 4.4 times 10 to the negative 12 times 6. You should get 2.65 times 10 to the negative 11. Again, we're solving for Q, which is in units of coulombs. Or you can even write this as 26.5 picocoulombs. And the last one, we're asked to determine the energy stored when it is fully charged. Again, fully charged means that the voltage across is equal to the voltage of the battery. So, our energy is going to be equal to 1/2 Q times V. We now have Q. Now remember, you could have also used the other equation for energy, but that one has a squared in it, and that's the one I tend to forget myself. So you can either derive it, or you can just use the information we now have. Which gives you 7.96 times 10 to the negative 11. Because we're solving for energy, this is in unit of joules. Now, we can talk about putting capacitors in circuits. And we have 2 different types of circuits, one of series and one of parallel. We know that we're dealing with a circuit in series when you have only one path to go from the beginning to the end. So we can look at point A here. And to go from point A to point B, I only have one path. Parallel circuits have multiple paths. So if I want to get from point A to point B, I could either take the top capacitor, or I could take the bottom capacitor. This means that there is more than one path, so I'm dealing with a parallel. And then we can have combination of series and parallel, which is our last example for this video. Here, we're looking at putting capacitors in the actual circuit. So, when 2 or more capacitors are wired together, the capacitance adds to form a sum of capacitance, or equivalent capacitance. What that means is if I have several capacitors, I can take those capacitors out and replace it with an equivalent capacitor, and nothing in the circuit would have changed. So, when adding capacitors in series, these equations might look familiar, but they are opposite of what we'll see eventually in resistors. So make sure to keep the two in mind. Again, when we're adding capacitors in series, we add the inverses. So we add 1 over C1 plus 1 over C2 plus 1 over C3. Now, the important thing is that we need to get the inverse after we've found the total. So remember to get inverses after. And then when you're adding capacitors that are in parallel, you simply add them together. Now, a few things we're going to have to remember, but we'll learn how to apply these again later. So capacitors in series will have the same charge. Again, we're looking at Q here. And their voltages will add up to the total voltage of the circuit. Whereas capacitors in parallel will have the same voltage, and their charge will add up to the charge of the circuit. And we'll see examples of what we mean by that in just a second. So let's look at this first example. Again, we just saw that our equation is Q equals C times V, where Q is charge, C is capacitance, and V is voltage. Here we have 3 capacitors that are in series. So to find the equivalent capacitance, we are simply going to add the inverses. So the first one is 2 farads, 4 farad, and 4 farad here. So to find the equivalent capacitance for capacitors that are in series, we do 1 over 2 plus 1 over 4 plus 1 over 4. Now remember to correctly add fractions. You cannot simply add the bottom. We need to find the common denominator and then add across the top. And then here, it's not as important to get an inverse because it's simply 1, but make sure that you do get the inverse. So our equivalent capacitance for 3 capacitors in series is simply 1. Again, our equation is Q equals C times V. So our charge is 9 volts. Actually, 9 coulombs, sorry. Because coulombs is a unit for charge. Again, our charge is going to be the same on all of my capacitors, and we'll see this in a lab. So, again, I have 9 coulombs across each of my capacitors. And then if I wanted to solve for the voltage drop across each of my capacitor, I simply do 9 divided by 2, 9 divided by 4, and so on, which is simply 4.5 and 2.25. Again, when you have capacitors that are in series, the voltages should still add up to give you the total voltage on your entire circuit. So we can double check that. And yes, we do get 9 volts if you add them all together. Here I have a slightly more complex circuit where I have 2 capacitors that are in parallel with each other. Okay. Again, we can tell that they're in parallel because as I leave my battery, I go across one capacitor. So again, only one path there, so that one's in series with the circuit. And then I come to this junction, and this junction tells me that I have 2 paths that I can take. Afterwards, if I take one path, I reach another junction, which means they're coming back together at this point. And then I go back to my battery. Again, this symbol here is a battery, but we'll see examples of that again later. So, the first thing you want to do is to simplify this as much as possible. So our capacitor 2 and capacitor 3, we can tell that they're in parallel, so I want to simplify those. So capacitors in parallel simply add up. So that will give me 8 microfarads. So I can make a separate column for this one if I really wanted to help simplify my circuit a little bit. Okay, now I can tell that this capacitor, the equivalent capacitor of C2 and C3, is 8 microfarads. That one is now in series with C1. So, in order to add capacitors in series, I simply add the inverses. Here I'm going to get 2 over 8, and then make sure that you get the inverse of it. So I get a capacitance of 4. Now this is my equivalent capacitance. So again, my equation is Q equals CV. So 6 times 4, 24 is my charge. Again, that charge of 24 is going to be the same on all my capacitors that are in series. So that applies to only C1. And then we can solve for the voltage, which is 3 volts. Now, we're going to learn a little bit more about voltage drops and Kirchhoff's rules later, but for now, we just want to apply that this 6 volts is for my entire circuit. So if I start here and I go through this one path, I need to use up that 6 volts. I've already used up 3 of them, so I have to use up 3 more as I go across capacitor 2. If I go through the other path, which is in green here, I also have to use up those 6 volts. Again, I've already used up 3, so I use 3 as I go through capacitor 3. And then you can solve for your charge. Here, 4 times 3 is 12, and 4 times 3 is 12. Again, you can see that these two charges are going to add up to 24. It makes sense because my charge you can think of as actual electrons. So when I get to a junction and that charge splits, I need to make sure I have that same charge at the end, my total. And then we'll see a little bit more of these in our lab tomorrow.